to share a bit about what we've been doing for the past 20 months or so. So Vova, Qiyuan, and myself have been building what I really believe is going to prove to be the future of auto-active verification. And I'm very excited to share the vision of what we're doing with you and share some of the lessons we've learned along the way. And my hope is that this talk gets you excited, it gets you to try Lean out, and maybe, who knows, gets you to build an auto-active verifier in Lean. That's what we've been doing for the past couple of years now. And we've been building this tool called Veil. And I assume most of you don't know what Veil is and haven't seen it before, so I will introduce it. And the keyword soup is that Veil is a multi-model foundational verifier for distributed protocols. This is not a very technical talk. So if you want the technical details, my colleague Vova will give a talk at Popple on Friday morning. So do attend that to get all the gory, cool details. This talk, however, is a bit higher level. And when I think about Veil, well, Veil for me is first and foremost a tool I built out of immense frustration at the state of existing tooling for verifying distributed protocols. And you can kind of plot the existing tools or existing approaches for this problem on this kind of plot, where the x-axis is the amount of time or effort you should invest to use these tools, and the y-axis is the benefit you can get by applying them. In terms of, say, number of bugs you can find or classes of properties you can establish, and so on. So the easiest and cheapest approaches, is concrete state model checking. And when it comes to distributed protocols, TLA Plus really is the king here. It's a very mature tool. It takes an expert maybe a couple of days to model a protocol in TLA Plus and model check it with TLC. It's very widely used in the industry, and so on. The problem with it is, even though in principle you can do proofs with it, in practice most people don't, because the tooling is quite bad for that. If you want to not just test your specification, but actually verify it, the tool to use for distributed protocols is this tool called Ivy. And this does SMT-based verification. And crucially, this is decidable SMT-based verification. So Ivy forces you to write your specification in a decidable fragment of first-order logic, which is very often possible for distributed protocols, but requires quite a bit of expertise to do. And once you do that, it lets you automatically prove your protocol correct, not just test it. And the fact that this is decidable actually gives you two major benefits. One is it makes the verification very consistent and stable. So you don't see the instability issues that auto-active verifiers usually have. And secondly, and just as importantly, and perhaps even more importantly, is it gives you a lot of tool support when verification fails. It gives you very concrete, clear counterexamples. And I'll show you an example of that a bit later when I give a demo. The alternative to this would be to use a tool like Dafny', which does general SMT-based verification. And people have been using these kinds of tools for distributed protocol verification. But the tools are more powerful, of course. But the power comes with cost. The cost is instability, and you don't get as much support when verification fails, which is the usual case when you're verifying a protocol. And finally, you have interactive theorem provers, and you can use interactive theorem provers to verify distributed protocols. These are very powerful tools. You can state any property you want. You can prove any property you want. You're just going to spend a lot of time doing it. So what people do in practice in industry is they kind of use the approaches on the left. So they use TLA a lot. And sometimes they might translate their specification to Ivy and do some proofs with Ivy, automated proofs with Ivy, use Ivy to come up with an inductive invariant. And you see there's this trade-off between expressiveness and automation. I don't like trade-offs very much. I want to do everything. So part of the trade-off, of course, is fundamental. You can't get around undecidability. But a large part of the trade-off is actually due to bad tooling. So what I want to do is I want to use all of these approaches in a single tool. What do you have to do now? What's the state of the art? Well, the state of the art is you kind of start with model checking and test your specification. And once you want to do more, well, you have one of two options. You either use a combination of tools, and that has issues around having to translate your specification and potentially introducing bugs when you translate to a different tool, or you add an interactive escape hatch to your automated tool, as we've seen in the morning session. I mean, it makes sense, but I think this is the wrong approach. And I've seen it happen so many times. I haven't tried the Dafny' tool, so I don't want to criticize prematurely. Maybe this is the tool that breaks this pattern. But all the other tools that add interactive escape hatches to automated verifiers are really, really bad in terms of user experience. I made this remark to my advisor, Ilya, a couple of years ago after seeing this happen again with another verifier, no Dafny'. And it seems like almost like a law of nature at this point, right? So I will postulate it as a law. Every verifier expands until it contains an ad hoc, bug-ridden, unusable implementation of half of an interactive theorem prover. Those verifiers which cannot so expand are replaced by ones which can. And I mean, it's a joke, right? It's kind of a joke, but it's also, I think, entirely true. And my work, if people are to know me for anything, I want people to know me for breaking this pattern. We don't have to live like this. There is a better option. It's called Veil, and it solved these issues. And the way we did it is really quite simple in principle. We just built the whole verifier in Lean. So rather than bolting on an interactive theorem prover to our auto-active verifier, we take the world's best interactive theorem prover and build a great auto-active verifier in it. So the proof is in the pudding. So let me show you what it looks like. Very quickly. You don't see my screen. Let me mirror. All right. So just as this morning, this is a Lean file. All you need to do to bigger. OK. All right. This is a Lean file. All you need to do to use Veil in a Lean file, you import Veil, and that makes available to you a DSL and a bunch of tools. So I don't have a lot of time. I'll mostly flash this. But the DSL is imperative language that lets you specify transition systems. So you specify the initial state, you specify the actions or transitions of the system, and then you specify the properties this system must satisfy. And then what does Veil let you do? Well, it lets you do everything you saw on that slide. It lets you do concrete state model checking. So let me introduce a bug in this protocol so we see kind of what this looks like. So that ran a concrete state model checking. And this is all Lean in VS Code. We didn't write any extensions. This is the regular Lean extension. Shows you a counterexample to the property we just broke in this protocol. Let me fix the protocol. And that was explicit state model checking. We can also do symbolic model checking in Veil. So here, let me make this bigger. We are doing a satisfiability query for a trace. So it's saying, well, there is a way of executing this protocol with any parameters, any number of nodes, such that you can take 3 actions, and at the end there's a leader. So we want to check whether this protocol is vacuous, right? And the solver tells us, well, yes, there is. Here's the trace. We can also do bounded symbolic model checking. Here we're saying we can take 5 actions, and then there's no way, basically, to elect 2 leaders. So this is a leader election protocol. This is a safety property. It says, well, yeah, no counterexample found. If we break the protocol, that will take a bit. This complains, and this will complain. And we see, a trace, a symbolic trace in this case, that shows 2 leaders being elected. OK, finally, and this is what I promised with Ivy-like verification, what does being in a decidable fragment of first order logic buy you? Well, it buys you inductive invariance. So let me fix the protocol again. And when you're verifying a protocol, the hardest part is coming up with the inductive invariant. So say we are in the process of coming up with an inductive invariant. What being in a decidable fragment of first order logic gives us is very nice counterexamples to induction. So here, the verifier is telling us, well, look, your protocol is not inductive. Your invariant is not inductive. Here's a concrete counterexample. So if you start in this pre-state that satisfies all the invariant clauses you've told me about, and you take this action, you get into a post-state that violates the invariant clause. So what this means is you must strengthen your inductive invariant with an extra clause to eliminate this pre-state. OK, that's all I have time for in terms of the demo. Let me go back to the slides. If that piqued your interest and you want to learn more, we're giving a tutorial tomorrow afternoon. I'd love to see you there. OK, so Veil is not fully there yet, but we want to have all of these approaches at your disposal in a single tool built in Lean. OK, so what have we learned besides the fact that you should build auto-active verifiers in Lean? Well, it's not all milk and honey in Lean land. So this was a sales pitch so far. The reality is it is very good. Like Lean is very good. It's a great tool for building verifiers. But you are going to face some hardship. So we learned a few things developing Veil. Some are quite obvious. So for instance, good software engineering practices are still things you should do when you build verifiers in Lean. So obvious stuff like testing. You need a lot of tests. It's hard to write correct programs. It's a lot harder to write correct meta programs. So you really need a lot of tests. And then things like modularizing your code and so on. So this is quite generic. I'm not going to dwell on this. More specifically, though, meta programming really is a two-edged sword. Meta programming has a steep learning curve. It took me about 3 months where I felt I had no idea what was going on, and then it clicked, and I felt like on top of the world. I can do everything. Everything is a meta program. I can implement anything. You can do anything you want. The fact that you can doesn't mean it's necessarily a good idea. So you can get yourself into really some unmaintainable messes with meta programs. Spaghetti code is bad. Spaghetti meta code, forget about it. OK. I'm going to expand on this on the next slide. The next 2 points are a bit technical. So if you're interested in the details, I'm going to be vague about them. If you're interested in the details, do read the manuscript we've put up. It's linked in the program. So it's nice to be shallowly embedded in Lean, as Velvet and Veil are. But you shouldn't be too shallowly embedded in Lean. So what I mean by this is if Lean constructs are interfering with your representations in your verifier, you're doing something wrong. You should control all your inputs to your verifier. Lean should be kind of a backend that you put definitions into, not, again, read a paper for details. It's a technical point. Slightly more general, but also a technical point, generality comes at the cost of complexity. So I've shown you a demo of Veil. You have all these tools at your disposal quite seamlessly in the front end. There's a lot of complexity on the back end to make that happen. And you, as a maintainer of a verifier, have to pay the cost of maintaining that and keeping it performant. And this is my last lesson. Performance is a huge issue. Like by far the biggest issue we have building auto-active verifiers in Lean is they are slow. Slow. I'll get back to this. Let me illustrate these 2 points a bit more at length. So what I'm showing here is the first version of Veil and the output of the check invariance command. So this is kind of what what you saw as a widget. And let's think about what this command kind of does. If you think about it, this is like 80% of the verifier. So let me go through the functionality of this command. So this goes through the Lean environment. It identifies every action you've declared. It identifies every property you've declared. It builds a lean expression that corresponds to every verification condition that this specification kind of incurs. It translates that expression from higher order logic to first order logic, sends it to an SMT solver, gets back the result from the SMT solver, prints the result, either green check mark or red cross with a counterexample, and then, because we're working in a foundational setting, for the theorems that succeeded, gets the proof from the SMT solver, CVC5, and reconstructs the proof in the lean environment. So you don't have to trust the external solver. That's a lot of things to stuff in a single meta program. And I mean, we kind of did stuff all of that thing in the original version of Veil in there, and it was a disaster. Like, it was completely unmaintainable. So for the second version of Veil, which we're about to release soon and which you've seen, things look a lot different. From the user's perspective, OK, sure, this is a nicer widget with incremental progress, but the backend is completely different. And the key insight, and I think this generalizes, is we found out that this model view controller architecture, which is very common in software engineering, makes a lot of sense for building verifiers. So the core of Veil 2.0 is this data structure called a VC manager. And basically the way this works, and I'm not going to go into details. If you're interested, do read my PhD dissertation when it comes out later this year. But the idea is the actions, the elaborators for the actions and the properties in your system put in obligations into this VC manager. The VC manager has logic for discharging these with external solvers, with, say, interactive tactics, and so on. And then checking variance is just a view. It just reads from the state of the VC manager, which does all of this asynchronously and displays a widget. Details in the paper. Finally, performance is a huge issue. So this is data that's almost 1 year old at this point, so don't look at the details. The gist of it is we're about 10 times lower than the closest comparable tool, IV. The largest chunk of it, so basically the blue and light blue chunks are overhead we incur because we're in higher order logic and we need to translate to first order logic. The green part is the solver time, right? So for very large specification, the solver time dominates, but we're still a lot slower than tools built the traditional way. That's the main challenge. We do hope that with more engineering, we can reduce the overhead to maybe 2, 3x. We're always going to be slower if we start with higher order logic and have to translate it to first order logic compared to a tool that just produces first order logic directly. But, well, you know, you take the good with the bad. That's all I have. Thank you very much. You can try Veil online on this online environment at try.veil.dev. So try it out on your laptop. Thank you. Okay. Can disconnect for the next speaker. Yep.
One question. Setup.
Thank you for an interesting talk. Could you comment on what is the link between Veil and Velvet?
Yes, they use the same semantic foundation. So basically, the semantics of Velvet and Veil are exactly the same, right? It's this framework called Loom, as is very much inspired by Dijkstra monads. You can more or less interoperate between the two. So they are, in some sense, the same core logical foundation with different instantiations.